After we have looked at Haskell, let's now look at the same example in JavaScript, although I will spend less time going through it because it's virtually the same. So if we start with JavaScript, then first we get some imports from Marlowe.js, and we see all the constructs that we have spoken about are also available here in JavaScript. And the way this works is that we have this function without parameter of type contract that returns the contract. So this basically replaces the main function in the Haskell version. So where the main function in the Haskell version prints a contract to the console, here in JavaScript, the way JavaScript returns the contract is via such a function without arguments. So this simplest program, if we compile it, would unsurprisingly just generate the close contract. And actually writing contracts here in JavaScript is very similar to Haskell. So we could just start, for example, with when, and we also get very nice autocomplete. So we see when takes 3 parameters, an array of cases, a timeout, and then the continuation, so the contract that happens if the deadline is reached. So I could now start, for example, with an empty array, and now I see I need a timeout. So for example, I could use time parameter again, and again I get nice help telling me that now I need a string, so the name of the parameter. And finally, I need this continuation contract. So for example, I could use close. And now this would also be a valid contract. It generates this Marlowe. And of course, now I could continue implementing our contract by doing the 2 deposits here. I could start with case that takes 2 arguments, the action and the continuation. So let's start with deposit and so on. Now I don't want to enter the full long Marlowe contract here in JavaScript, but you get the idea. And actually the support with auto-completion is really very nice. It's actually nicer than in Haskell. So you always get help, context-sensitive help. So instead of repeating step by step what I did in Haskell, I'll just show you the result. And this is also saved on a public gist. So we will leave the link to that in Canvas. So this is virtually exactly the same simplifications and refactorings that I did in the Haskell version. So I have a parameterized function that produces a contract that I call double pay with the same parameters we had in Haskell. So the 3 parties, the amount and the deadline. Then I have helper functions here, pay and deposit and deposits. Then using these helper functions, it's easy to write the actual contract. It's just one when with 2 cases, deposits giver 1, giver 2, and deposits giver 2, giver 1, deadline and close. And then finally, by instantiating the parameters to the values we use, so role giver 1, giver 2, receiver, the deposit param, and the time param, I get exactly the same contract that I had before. So I can compile, and this should be exactly the same Marlowe contract we have looked at before. And it seems to behave the same as it should. So it's really a matter of taste whether you prefer JavaScript or Haskell. I personally prefer Haskell, of course, but if you are more familiar with JavaScript, then it's perfectly okay to write your Marlowe contracts in JavaScript. As you can see, you can do basically the same simplifications that I showed you in Haskell, also in JavaScript, and end up with a version of the contracts that's just as short as the Haskell version was. So to summarize, we can write Marlowe in JavaScript and in Haskell, and the principle is the same. You write a Haskell or JavaScript program, that produces a Marlowe contract. And you can use all the features of the host language, Haskell or JavaScript, in order to produce that contract. So in particular, you can make use of features like local definitions, helper functions, and so on to make that task easier and make it shorter. And of course, by preventing code duplication, you also prevent mistakes. I mean, it's a common mistake to want to write the same code, but then actually not ending up with the same code. So by refactoring that and pulling out the common parts, you avoid that common source of mistakes. And as I also mentioned, you are not restricted to JavaScript or Haskell. So in principle, you can use any language you like as long as you can produce some JSON. So if you produce JSON, that's serialization of valid Marlowe contract, then you're fine, and it doesn't matter what language you use to produce that JSON. In the example I showed you, we used Haskell or JavaScript to drastically reduce the amount of code we had to write by removing code duplication. But the end result, the resulting Marlowe contract that was produced by our Haskell, respectively JavaScript program, was exactly the same that we wrote before, for example, in Blockly or in Marlowe directly. So in that sense, we didn't gain anything. I still think, especially for more complex contracts, it's much easier to do it like this in Haskell, JavaScript, or another language. But nevertheless, the result we got was exactly the one we could have written in Marlowe directly. So now I want to talk about use cases where actually you need to do it like this in order to achieve your objective. And that is the case when the structure of your contract depends on the specific instantiation. So the contracts we wrote, especially this example contract, had two parameters, the deadline and the deposit. So in that sense, it was not just one contract, but a template for contracts. You can choose a specific deadline and a specific deposit amount, and then instantiate your specific version of the Marlowe contract, the instance of your Marlowe contract, to those values of the parameters. But what if the structure of the contract itself is supposed to be parameterizable? So in our example, we had these two givers that have to deposit the same amount of money into the contract. And then once they both do that, the money is sent to the receiver. So let's now assume that you want to generalize that. So you want to maybe have three givers or five givers. So the logic should still be the same. So given a fixed number of givers, which can be two or more, those givers have until the deadline to deposit a given amount into the contract in arbitrary order. And once all of them have done it, the receiver gets all the money. Of course, you could do that for any specific number. So we did it for two givers. Of course, you could do it principle for three givers or for four givers or for five givers. But of course, it would become more and more complicated. Now we needed two cases in our when statement, in our top level when statement. One for first giver one deposits, then giver two, and another one for giver two, giver one. Now, if you have three givers, then there are already six possible orders in which these deposits can happen. So in principle, you need six cases, or rather you need three cases at the top level for whoever is the first one to deposit. And then in each of the three cases, you need two more cases who will be second and third. If you have four givers, it would be 24 possible arrangements of deposits. So four at the top level, then in each of those four, three, in each of those 12, two, and so on. So you can see it gets more and more complex. And of course, you could do that in Marlowe or Blockly directly, but it would become very unwieldy. And it's also not general. You would have to do each of those cases separately. So let's say I've implemented it for three, then that doesn't help you very much to generalize it to four. You would have to do that completely new from scratch, basically. And by using Haskell or JavaScript or another language, you can actually write a program that can produce such Marlowe contracts for an arbitrary number of givers. Of course, not really arbitrary because there are size limits, but at least for like a small number of givers. And that is something you simply can't do in Marlowe directly. You can do it for a specific number of givers, but you can't generalize it for arbitrary number of givers. You do have these parameters, so certain things you can generalize, but that's only restricted to values and timeouts. Can't keep the structure of the contract itself flexible. So now I want to show you how in Haskell we can actually generalize this contract to an arbitrary number of givers.